Hello space enthusiasts. Welcome to GenexSpace This program focuses on discussion of the hot topics in space like James Webb Telescope, understanding the first image of the black hole, and all the latest and hot topics of space science, where anyone and everyone are welcome to join and start a venture of understanding the latest happenings in the space industry. So this will be a bi-weekly program where every second weekend we will have a topic to discuss about, and like twice a month. So my name is Garvit. I work as an educator at GenexSpace, and let's begin our journey of discussion of the hot topics of space. So today's topic will be James Webb Space Telescope. So what is James Webb Space Telescope? Who made it? Who launched it? I mean, what is it for, and why is it such a big deal? So many questions about the James Webb Space Telescope right now going on in the science industry or space industry, right? So James Webb Space Telescope, who made it? For the who? It is a joint venture of NASA, Canadian Space Agency, and European Space Agency. So these three space agencies came together and made the James Webb Space Telescope possible. As to how, it was launched by the European Space Agency's spacecraft in French Guiana. So this was the rocket that was used to launch the James Webb Space Telescope, and by rocket called Ariane 5. So James Webb Telescope was launched on 25th December 2021 at 7:20 AM European Standard Time. But actually this was supposed to launch in 2016 only, but space industry, many things happen. There are happenings, one things led to the other. So for 2000, it was supposed to happen in 2016, but it took almost 4 years to finally have a successful launch, and it launched in 25th December 2021. And it started its function on 12th July 2022. So almost 4 months later. So why it took 4 months? Why it took such a long time to launch and start its process? We'll discuss about it. So the main objectives of James Webb Telescope was not this glitch, but the main objective was James Webb Telescope first objective was to find the galaxies that was first formed just after the Big Bang. So it is such a powerful telescope that the galaxies which were formed just after the Big Bang, the very first galaxies, this has the power to see the images of those galaxies. And the second major thing that James Webb was designed to do was to look for extraterrestrial life forms, like to find exoplanets, right? So this James Webb Telescope had so many missions to it, so many functions to it. So many people think that the James Webb Telescope, once James Webb Telescope is here, it was a successor of Hubble. Like once James Webb is out there, Hubble will no longer be in use. But that's not the case. Actually, James Webb Telescope and Hubble Telescope are working together for understanding of outer space of the universe. So how are they working together, and why is it that we need both of the telescopes? So the first difference between James Webb and Hubble is that if you look at this, that this is a scientist, and compared to this scientist, this is the size of the Hubble's primary mirror, and this is the James Webb mirror, a huge mirror of 6.5 meters, right? So it is a huge mirror compared to James Webb, Hubble. But we need Hubble also, because Hubble has the primary function in the visible spectrum. So Hubble only captures those images, those rays of the universe which are in the visible spectrum. But James Webb captures in the infrared region. Okay. So because we need both the images, we need visible spectrum also, we need infrared also. So we need both the telescopes to work with each other. Okay, but why do we need infrared capturing telescope? So the thing is, there is a thing called redshift and blue shift. So what is redshift and blue shift? So because the space is expanding, right? So the whole universe is expanding at a great speed. I mean, there are speculations that it is expanding greater than the speed of light also. So because it is expanding at such a great rate, so the light that is coming from these galaxies, they are literally stretched apart. Okay, so because the whole space is being stretched, the light that is coming from the space is also stretched apart. And because these lights are being physically stretched in size, so the wavelength of these lights gets stretched, and as you can see that the wavelength is increasing. See, as we go from gamma ray, then X-ray, then ultraviolet, then this little spectrum here is the visible spectrum, and then infrared and radio waves. So as we go from one phase of light to the other, the wavelength is increasing, you can see here. So because the galaxies which the James Webb was supposed to see are so far away in the universe, that the light that is coming from there have moved past the visible spectrum also. So the visible spectrum ends here at the red color, right? But because these galaxies are so far away that their wavelength have stretched so much that it has passed the visible spectrum and it has moved to the infrared region. So that is why we need an instrument that can capture images in the infrared spectrum. So like this image. This was the first infrared image that James Webb sent us. This was the very first image that James Webb has sent to us for seeing that how powerful James Webb actually is. Like if you see this image, this was by the Spitzer Space Telescope and this was by James Webb. You can see these both are the same patch of sky. These 4 stars here and these 4 stars here. But the kind of resolution, the difference in the resolution you can see in both these images. James Webb is so much more powerful than any other space telescopes that we have sent yet. So you can see that even the stars that are behind these gas clouds are also visible to us, just because it is viewing the space in an infrared spectrum, right? But when we see this image, the major questions that arises is, first is that what is this black hole in the center, right? Why is there a black patch or black hole in the center, and what are these spikes? So these spikes are called as diffraction spikes. Okay, and talking about the black hole at the center, that is not actually a black hole at the center, that is just a dark patch. Why that dark patch happens is because we use a phenomena called as coronagraph. So what coronagraph does is, because James Webb is mainly focused on finding exoplanets and new life forms. So but whenever there is an exoplanet that is revolving around a star and it comes in front of the star, there is a huge glare of the star that we have to see. That the huge glare of the star is just making those exoplanets out of focus, right? So we need a way to block that glare, and coronagraph is just the way where we can just block the star, where all the glare that is coming from the star can be blocked and the exoplanets can be clearly visible. Like this, why it is called coronagraph also? Because this image you can see, these are the atmosphere of the sun. Okay, this atmosphere of the sun is called as corona, and the coronagraph at the center just blocks the main portion of the sun, because of which the atmosphere is clearly visible. Not only atmosphere, you can see that the white stars at behind, those are also visible just right behind, just right in the venture of the sun, right? So this is why we use a coronagraph, so that the main glare of the star can be blocked and we can see all the things that are around it more clearly. That is why those dark patches at the center of those images. So when we have launched the James Webb, it started little slowly it calibrated all its instruments and all its mirrors and everything. So during its calibration only, it used all its instruments so that it can see whether or not all the instruments are functioning properly and it is ready to see the universe in a new way. So this is the calibrating of the mirrors to the secondary mirror, so that it has a focus light at the secondary mirror. And about those diffraction spikes, what are those spikes coming out from all the stars? Those are because of the shape of the mirrors. So because James Webb is shaped in this hexagonal pattern, that is why you can see that these yellow lines are because of the James Webb mirrors, and these blue lines are of the struts that is holding the secondary mirror, like the stand for the secondary mirror. So both of these things combine together and make these spikes. So you can see here that every shape of mirror that has some diffraction spikes in it. Like if it is a circular mirror, it will have a circular image. If it is a hexagonal mirror, it will have a hexagonal spikes. You see these six corners at the hexagonal? These are the 6 spikes that are there because of these 6 corners of the hexagon. So as we move from one thing to the other, you can see that the James Webb telescope has these tiled hexagons, then these tiled hexagon with gaps, and then this is the James Webb telescope. And this is the image that is produced because of it. So it is not only that only James Webb has these spikes. You can see this image, that this is the image of a very famous image called as the creation, pillars of creation, right? This was captured by Hubble. And you can see here that this also has these spikes. All these stars that are there, all these also have these 4 spikes at the corners, right? So why these are there? This is because even Hubble has these struts. Even Hubble has these struts, the 4 struts, that is why those 4 spikes, right? So it is not only that James Webb has those diffraction spikes in it, every telescope has some or the other diffraction spikes in it. Okay, like this image, this is the, you can call it a before and after image of James Webb and Hubble. So the image that is not very clear, that is of Hubble. You can see these 4 spikes, and then we come to James Webb, you can see these 6 spikes of the hexagonal pattern. So this is the same patch of the sky that both James Webb and Hubble were seen, and this is the major difference in the power of James Webb and Hubble. See the clarity of the image that James Webb has sent us other than Hubble, right? So James Webb is a very powerful telescope in this field. Or like this image, this is called as the Crying Nebula. So this was captured by Hubble also and captured by James Webb also. But see the level of difference in the clarity of both Hubble and James Webb, right? So there is a huge difference in power. But because James Webb captures in infrared region, it has these so many advantages to it, but it also has some disadvantages to it also. The major disadvantage of capturing rays in infrared region is that the hot objects also emit infrared rays, right? And the hottest object that is there in the solar system, it's our sun. It emits almost 50% of infrared energy. So all the energy that is emitted by the sun, 50% of it is just infrared energy. So we need a place to place the James Webb in such a region of our solar system that solar energy is not very much visible there, so that much noise is not there in the images, right? And what is a place in the solar system where solar rays are not there? Can you guess, anyone? Any place that solar rays are not available at that place? That place is the shadow of Earth. So what we did was, we sent the James Webb telescope to such a place that is all that it always is in the shadow of Earth, right? And that place even has a special name called L2. So this is a place that is always in the shadow of Earth, so that noises from the solar radiation or solar infrared rays are not visible in the images of James Webb. But again, there is a question that if we just block the James Webb telescope directly in the shadow of Earth, how will it have power to function of it? Because it needs solar energy to function and to perform all its functions, right? It needs solar energy to perform. So for that, we placed James Webb not just in L2, but in a halo orbit around L2. So it is not just at a single place, it is in a halo orbit, okay, so that it can have all the necessary solar energy required for its function, but also it has enough radiation that it is blocked by the sun, okay. So even after placing it so far away in L2, that these are the five points in space that are in any binary system, like Sun or Earth, or Sun or Jupiter or its planets, or Earth and Moon. So any binary system has these 5 points in it called as Lagrange points. Okay, so there are basically 5 Lagrange points called L1, L2, L3, L4 and L5. And how do we decide what Lagrange point do we use? So here you can see that L4 and L5 are the most stable Lagrange points. Okay, so you can see that it's a huge place in L4 and L5 where things can be there and it can be in stable positions. But L1, L2 and L3 are metastable points. So what a metastable points is that even a little push at these points, L1, L2 or L3, it will, if the push is towards the sun, it will just venture into the gravitational influence of the sun, and if the push is the other way, it will just venture out into outer space. So it has to be a very stable position so that it is continuously configured in these places. So if you can see this, that this is the moon and this is James Webb telescope, almost 1.5 million kilometers away, right? So far away from the moon also. And a fun fact about moon is that moon is so far away that you can place every planet between Earth and moon and still there will be place for Pluto. So the moon is still so far away and we have placed James Webb so far away from the moon also. So just imagine the level of things that we needed to secure it from, right? So we placed James Webb in this halo orbit around the L2 point, and even if some of the rays of sun is still there, we shielded it from the sun by using this sun shield. So only the rays that are useful for James Webb to perform its function are only there, and no noise is there in the images of James Webb. And we painted this sun shield for pink for some reason. So we provided this sun shield and we are good to go then. So this is the size of James Webb telescope that is to compare, right? So these are the scientists that were involved in the making of James Webb, and this is the size of James Webb. So how did we send this tennis court size of thing into space, right? How did we send this whole thing into outer space? The answer may surprise you also, because it is a very ancient method of using this. So we use a method called origami. If you have heard this method, that this is the same method which we used as a child to fold the paper into many different shapes like animals or many other things, right? So this is the exact same method which we used in the James Webb telescope also, the origami method. So what we did is we crumbled up the whole telescope into the top payload section of the Arena 5 rocket, and we launched it into space. And when it ventured out into space and it got ejected from its rocket, it slowly opened up in its whole pathway to point L2. Okay, so after 3 days its sun shield opened up, after 10 days its secondary mirror support opened up, and slowly it went to the point L2 and started its venture. Okay, so this is the pathway that James Webb took, that when it was at Earth, it swirled around the Earth for some time, then it went to the other portions of space and went to the point L2, 1.5 million kilometers away. It's a huge distance to cover, right? So as it got to the point L2, slowly on the way, it opened up, it unfolded itself, and it started its function, right? So it started sending us these beautiful images of outer space, like this image. This is the Crab Nebula. Many people must have seen this Crab Nebula, but they must not be recognizing it, because the thing is, this was captured in the infrared region, right? This was captured by James Webb, and the Crab Nebula image that we are already familiar with is this one. This was captured by Hubble Space Telescope. But the thing about the difference about this Hubble image and James Webb image is that in this image it is not very clear that this is actually a binary system. See, the whole nebula was a binary system, and we just now came to know about it. So this was the power of James Webb Space Telescope. These images were recently published by NASA to the public, right? And we came to know about these things. And these beautiful images of these deep field images, you must have seen these images. They were recently in news also, and people say that this is the image that must has the light of the oldest galaxy that was formed just after the Big Bang. This is the same image that will have that light. So the hunt is on. People are searching for those old light, those red shifted light, so that they can have the image of the oldest galaxy ever formed after the Big Bang. Okay, so these images are clearly these images are clearly very in the visible spectrum, right? So as I have said that it is infrared rays, right? So how are these images in the visible spectrum? So the thing is, James Webb also captures these images in the visible spectrum. We see that those images in visible spectrum because it captures images just as a normal camera also. So that as a normal camera captures images in the visible spectrum, like you can see this, it captures images in 3 wavelengths, that is red, green and blue. So it combines all those 3 wavelengths of light and give us a full color image. Okay, so like this also, James Webb also collects all these 3 images, all these 3 wavelengths, but not in visible spectrum, but in the infrared spectrum. Okay, so infrared spectrum also has these certain wavelengths to it, right? Like in the visible spectrum, we have red, green, blue, all these different wavelengths of colors. Infrared also has these different wavelengths of colors, right? So James Webb telescope captures these 3 different wavelengths of images, which then combines together by its all the instruments that are on board, like this MERI instrument or CRS-RI instruments, and these instruments captures these images in all these different wavelengths of lights and combine those images together to form an image that is a visible in the visible spectrum, right? These are legit images that will be visible if you go out into space, right? So these are not just some artistic representations, these are legit images that James Webb captured by its infrared cameras. Just the difference is that this is not in the visible spectrum but in the infrared spectrum. Okay, so James Webb has just begun its journey to venture into outer space, right? It will give us beautiful images in the future. It will give us the latest, or the not the latest, but the oldest light of the universe, and the formation of the first stars, the formation of the first galaxy, how galaxies evolved, and everything. James Webb will tell us all these things in the coming future. Like one of the images that James Webb has given us, that there are speculations that in that deep field image, remember, there is already a light of the oldest galaxy. People have searched for that, and there is actually a candidate for the oldest galaxy in the universe, that is called as GenexSpace. So this is a candidate for the oldest galaxy in the universe, but this is just a candidate because it is not spectrographically confirmed. There is another candidate called Z10. So that is also one of the oldest lights in the universe, but again that is also not spectrographically confirmed. So still the candidate, not the candidate, but the confirmed image of the oldest light or the oldest galaxy in the universe still holds to the James Webb telescope, which is ZN1311. Okay, so this is still the confirmed image of the oldest galaxy, which was again taken by Hubble Space Telescope. But future has it, James Webb is a powerful telescope. It will start giving us more and more images in the future, and who knows, it may also find us an alien life forms, because the main function of James Webb telescope is to find extraterrestrial life forms. So it will start giving us the images of exoplanets, the images of extraterrestrial life forms, maybe, who knows, and it will be our one and only, not one and only, but the most powerful telescope to be ever built. So this was the weekly space chat, the first session of the bi-weekly space chat by GenexSpace. If okay, so GenexSpace provides topics like astronomy, astrophysics, aeronautics, cosmology, aeromodeling, rockets, satellites, astronauts, space laws, future opportunities, careers in space, field trips, entrepreneurship, you name it. Okay, so if you are interested in any of these topics, you are ready to start your adventure in the understanding of the cosmos and the understanding of the aerospace industry, you are free to join us. You can go to our website of www.genex.space and start your venture in understanding of the cosmos. Thank you.